Okay, let's dive right into this. Welcome to today's explainer, where we're going to take what might seem like super tedious math and transform it into, honestly, an empowering investigation. Look, if you've ever stared down a massive, complicated polynomial function and felt a sudden wave of panic, hey, trust me, we have all been there. You are in exactly the right place. Today, we're not just doing raw calculations. We are assembling a detective toolkit. We're going to learn how to extract the hidden clues right out of the math itself, which is going to let us sketch these complex functions by hand completely from scratch.
So ask yourself, could you sketch a complex polynomial without ever touching a graph and calculator? I know. A long equation with all those varying exponents and coefficients looks ridiculously intimidating. It is so tempting to just punch it into a device and let the silicon do all the heavy lifting. But the thing is, doing that totally robs you of understanding the why and the how. Today, I'm promising you a toolkit that will let you crack this mathematical case entirely by hand, using nothing but pure logic and deductive reasoning.
Here's our roadmap for this explainer. 1. We'll talk about ditching the graphing calculator. 2. We'll build our 8-step strategy. 3. We'll put it all together by cracking a specific case. 4. We'll master the intermediate value theorem. And 5. We'll explore some real-world uses.
All right, part 1. Ditch the graphing calculator, moving from guessing to accurately sketching.
We're replacing that reliance on technology with pure deductive logic. Because when you rely on a screen, you're really just getting a snapshot. But when you sketch it yourself, you understand the entire anatomy of the function. You see, every single polynomial function is packed with hidden algebraic clues. And once you know how to read them, there's absolutely zero guessing required to draw them accurately. The most fundamental clue about polynomial graphs is just their physical nature. They're always smooth and continuous. That means no holes, no sudden jumps, no random breaks, no asymptotes, and absolutely no sharp corners. Imagine a roller coaster track winding endlessly left and right without ever breaking. That continuous flow is exactly what we're drawing.
Moving right along to part 2, the 8-step strategy, assembling your math detective toolkit.
Finding these algebraic properties is exactly like sweeping a crime scene for clues. If you miss even one, your whole picture might be completely off. So this organized strategy ensures we don't miss a thing. The very first things we're looking for are the degree and the leading coefficient. The degree, which is just the highest exponent in the polynomial, is incredibly revealing. It literally tells us the overall shape, the maximum number of real zeros, and the maximum number of times the graph can turn. And when we combine that degree with the leading coefficient, that's the number attached to that highest exponent, we use what's called the leading term test. This test tells us the end behavior, meaning as the graph goes off infinitely to the left and to the right, does it point up to the sky or down to the ground? Now, what's really interesting about this is how these elements interact. If the degree is even, both ends of the graph go in the exact same direction, kind of like arms raised in victory or both arms pointing down. But if the degree is odd, the ends go in opposite directions, like a dancer with one arm up and one arm down. Then, the leading coefficient steps in as the final judge. A positive leading coefficient generally means the right side of the graph is going to rise. A negative leading coefficient, the right side falls. So just by mixing these specific combinations, you instantly know the outermost boundaries of your entire sketch.
Okay, so once you know where the ends of the graph go, you kind of need to know where it crosses the middle, right? We do this by setting the whole function to 0 to find our x-intercepts, also known as the zeros. But finding the 0 isn't quite enough. We need its multiplicity. Multiplicity is just how many times a specific 0 occurs when you factor the polynomial out. If a 0 has a multiplicity of 1, the graph slices right through the x-axis. If it has an even multiplicity, like 2, the graph simply touches the axis and bounces right back. And if it has an odd multiplicity greater than 1, like say 3, the graph flattens out slightly right as it crosses the axis. It adds this whole new layer of precise detail to our sketch.
To wrap up our toolkit strategy, you should always consult this 8-step checklist before your pencil ever hits the paper. What is the degree? What's the leading coefficient? What is that end behavior we just talked about? What are the real zeros and what are their multiplicities? Oh, and don't forget the y-intercept. Just plug in 0 for x to find exactly where it crosses the y-axis. Calculate your maximum turning points, which, handy tip, is always just your degree minus 1. And finally, review your sketch. Does it actually satisfy every single property you uncovered? Using this checklist is your safeguard. It prevents vital information from slipping through the cracks.
Let's move to part 3 and see how this builds. Putting it all together, cracking a specific case.
It's one thing to look at abstract rules on a checklist, but it is another entirely to apply our toolkit to an actual complex polynomial. So here's our target, f of x equals x cubed minus 4x squared minus x plus 4. Now the crucial point here is, do not panic. Seriously, do not reach for that calculator. We're just going to methodically follow the clues we just learned.
Let's walk through our logical steps together. Step 1. The highest exponent is 3, so the degree is 3. That immediately tells us the graph has at most 2 turning points. Step 2. It's an odd degree with a positive leading coefficient of 1. That means the graph is going to fall to the left and rise to the right. Step 3. We need our zeros. If we set the whole equation to 0 and use factoring by grouping, it actually factors beautifully into x minus 4 times x minus 1 times x plus 1. This reveals our zeros are at positive 4, positive 1, and negative 1. And hey, since each factor only appears once, the multiplicity is 1. That tells us the graph simply crosses the x-axis at each of these 3 points without bouncing or flattening. Step 4. We find the y-intercept by just plugging in 0 for x, which leaves us with a positive 4. So we plot a point right at 0, 4. Now we just take all these clues, the falling left and rising right ends, the 3 specific x-intercepts, the y-intercept, and the maximum of 2 turning points, and we simply connect them with a smooth, continuous curve. Boom, case closed. You literally just sketched the cubic function entirely by hand.
Which brings us to part 4, the intermediate value theorem, or what I like to call the continuity cheat code.
So what happens when a polynomial doesn't factor perfectly like that last one? What if we run into a situation where finding the exact zeros is practically impossible to do by hand? Well, we use a conceptual cheat code. Picture this. You are out for a hike. You started at an elevation of 20 feet and you finish at an elevation of 80 feet. Could you possibly hike up that hill to reach the top without ever crossing an elevation of 50 feet? I mean, of course not. Unless you've got a jetpack or a teleportation device hiding in your backpack, your physical path up that hill is continuous. You literally have to step through every single elevation between 20 and 80 feet to get there. And honestly, this makes the concept of mathematical continuity instantly intuitive and relatable.
That hiking analogy? It perfectly describes the intermediate value theorem, or the IVT for short. Since we know polynomial functions are continuous, meaning they have absolutely no breaks or jumps, they behave exactly like your hike. The IVT states that if a continuous function has opposite signs at point A and point B, there absolutely must be at least one real zero between them. Think about it. If the graph goes from a negative y value down below the x-axis to a positive y value up above the x-axis, that continuous line has to cross the x-axis at some point. And that crossing point, that's our zero.
And this brilliantly illustrates the sheer power of the IVT. Notice, we don't even know the massive equation behind this data. All we know is that when we input an x of 1, our output is positive 5. When we input an x of 3, our output drops to negative 2. Because the signs are opposite, flipping from positive to negative, we have visually and mathematically proven that a real zero absolutely exists somewhere between x equals 1 and x equals 3. We didn't even have to solve the complex equation. The theorem did all the heavy lifting. One super important note though, a sign change guarantees a zero. But if the sign didn't change, let's say it went from positive 5 to positive 2, you cannot conclude there's no zero. The graph could have dipped down, crossed the axis twice, and popped back up. The theorem just guarantees a zero when those signs flip.
Finally, part 5, real-world polynomials, math in the wild.
So why does any of this actually matter outside of a math classroom? Let's ground this abstract theorem in reality for a second. Say the temperature of a chemical solution drops from 5 degrees Celsius at 9 a.m. down to negative 3 degrees Celsius at 10 a.m. Did the temperature of that chemical ever hit exactly 0 degrees? Well, because temperature changes continuously in the natural world, it doesn't just magically teleport from 5 to negative 3, it's a continuous, smooth drop. By applying the intermediate value theorem, because the values changed from positive to negative, we can definitively guarantee that the solution reached exactly 0 degrees at some specific moment between 9 and 10 a.m. These mathematical clues perfectly predict and map the continuous natural phenomena happening all around us every single day. So the next time you watch a stock market chart plunge or track a storm system moving across a radar map, ask yourself, what invisible mathematical zero did that continuous system just cross to get there? Keep investigating, and I'll see you in the next explainer.